Today we are going to start our review before the second midterm. As I mentioned before, the second midterm will cover highway vertical alignment and the fundamentals of pavement design and construction. As I mentioned before, the highway vertical alignment is basically, it's composed of a group of tangents that we make to smooth the ride of vehicles over the natural ground level. Of course, as we can see in this image, we cannot, this kind of rough terrain, it's not suitable for, regular cars to drive over, and it's also the bearing capacity for the natural soil, it's not sufficient to carry heavy loads like trucks and so on. That's why we build, make this vertical alignment, okay, to smooth the ride, first of all, and we build the pavement to distribute the load over the natural soil. So basically, the vertical alignment is composed of group of vertical tangents connected with curves. These curves, the objective basically of the vertical alignment is to minimize the cut and fill, and the constraint is to maintain acceptable level of service and capacity. The grades, these grades, the grades of these roads or these tangents should be suitable for the design vehicles and the passenger comfort. So, as we mentioned, for passenger cars, 4 to 5% grade, this does not affect the performance of passenger cars. But for trucks, that means a lot. It affects the speed significantly. And we have discussed this chart. This is for trucks, entering at speed of 90 kilometers per hour with a weight to power ratio 120 kilograms per kilowatt hour. Okay, we discussed this before, and we discussed the issue of climbing lanes, and these are the criteria for climbing lanes. These three criteria must be satisfied. The first one, that we have sufficient traffic volume. The second one, that we have the acceptable number of trucks per hour. Then one of these criteria, either speed drop is greater than 15 kilometers per hour, or there's a drop in the level of service to the level of E or F, or there's a severe drop in the level of service by 2 or more levels. For example, if it was A and at that grade it became D, this is not acceptable. But if it was A and became C, okay, 2, this is a 2-level drop. Okay, so also this one is not acceptable. But from A to B, this is acceptable. Okay, so if the drop in level of service was 2 or more, then we must make a climbing lane. That was an example, and that's a chart we are demonstrating here, that under this line, which is the 75 kilometers per hour, this corresponds to a drop of 15 kilometers per hour in speed. Under this red line, in this area, we need to have a climbing lane. Above this line, we don't need to have climbing lanes for trucks. We showed here that the sequence of grades affects the performance. Even, both are the same. But here we have 3%, 6%, and we demonstrated that the exit speed here will be significantly lower than here. Then we started talking about vertical curves, and we have two types basically of vertical curves. We have crest vertical curve and we have sag vertical curves. The main objective in the vertical curves design is basically to have the driver. Okay, before we go to that, there is a fundamental difference between vertical curves and horizontal curves. Vertical curves are basically it's a parabola. It's a second order, equation, as we can see here. But the horizontal curves are part of a circle. Okay, so the parabola here, it can be said that the length of the curve equal to the chord of the curve. Okay, so it's not significantly different. Okay, and some might not accept that, but basically that's due to this angle is very small. It's not like in the horizontal curves. So this angle is negligible. If you try to evaluate this angle, how much this angle, let's just, for example, if we say that we have 4% and 8%, okay, so how much is theta? If you calculate that, so this angle is tan inverse 0.04, it's 2 degrees, 29, and the angle here will be 4.5. So that means this theta equal 6.86 degrees. At this small angle, if you measure the arc length, okay, and the direct chord length, both will be almost the same. Okay, for example, if we have a vertical curve that has the length of 500 meters, what's going to be the radius? The radius will be, let me just move this to a second page, because some of you are usually get confused with this issue. It was 6.86. If we say that we have L equal 500 meters, okay, then the radius for this will be L equal R multiply theta. So R equal L over theta, but theta in radians, by the way. So that means it's 500 divided by 6.86 multiplied by pi divided by 180. So if we multiply this by pi divided by 180, then multiply 400. Okay, so the radius in this case would be 4,173 meters. That's R. So let's calculate the chord here. The chord here would be basically theta over 2 R theta over 2 sine theta over 2. So it's 2 R sine theta over 2. Let's see how much will be this. Multiply 2, multiply sine 6.86 divided by 2. So this chord length would be 499.41. You can see now that it's almost 500. Let's see the tangent. The tangent length. How much does it equals r tan theta over 2. Okay, so we have 4173 multiply 10 6.86 divided by 2. It's 250.11 meter. That means the difference is 11 centimeters. So it's negligible difference. شايفين يا شباب؟ That's why we use the parabola instead of, or we use this form instead of the equations for a circle. Correct? Everybody get the point?
Yes, doctor.
Okay. I think most of you were wondering why we are using this form. We are not doing the same like horizontal curves, right? But the main reason is that the angle here is negligible. It's very small. So the difference between the tangent and the chord length and the vertical curve length are almost negligible. Okay. Here, for the shown curve, determine the station elevations for BVC and BVI. Okay. When we ask for designing a vertical curve, what we are looking for? We are looking for, number one, L. Excuse me? We are looking for curve length. That's number one. Number two, we are looking for the BVC, point of vertical curvature, and point of vertical tangent in terms of stations and elevations. Okay, so that's for crest. If it was a sag, then we need to do checks. This, what we imply with designing a vertical curve. Okay, so what is the design criteria for sag, for crest curve? The main idea here is to design the curve with the proper length such that if there's a driver trying to cross the curve, okay, he still be able to see an obstacle, okay, on the other side of the curve that has a height h2 equal 0.6 meters, okay, and able to stop. So that means when the driver here sees the vehicle, the distance should allow this driver to stop the vehicle. So the stopping distance should be, so in order to satisfy this, if the stopping distance was less than L, then we use this formula. Okay. If the stopping distance was greater than L, then we use this formula. So how can we do that? We start first assuming that S is less than L. Then we substitute here. If L, okay, becomes less than S, then we go to the second formula. So here, this is a short term. This is basically the same form here, but after substituting for H1 and H2 with 1.08 and 0.6. Okay, so H1 1.08, that reflects the height the eye of the driver in an average sedan car. H2, that's the height of the obstacle on the other side that we are trying to avoid. Okay, the other category of curves, which is basically the sag curve. Okay, so the design criteria, we have here 4 design criteria. The first one is the headlight stopping distance. We are not counting here on the driver's eye, because the driver's eye you can see all the way. But the design criteria for these, for sag curves, basically we take the case of of driving at night, and the angle that the headlights covers is basically shifted from the axis of the vehicle by 1 degree going up. So this basically the distance, okay, that is visible for the driver or covered by the driver. So this distance should equal or to the stopping distance. So that's the headlight stopping side distance. And we need to take into consideration the passenger comfort, the drainage control, the general appearance. For example, in the Crest curve, we didn't talk about drainage because basically water will fall on the sides of the crest. But in the sag curve, it's very common that we get pools of water if there was poor drainage and it's not designed correctly. So this is a dry, the passenger comfort, that's another important, the degree of curvature should be comfortable to the passenger. It's not, like an amusement park or something like this, sharp curve. We don't want drivers and passengers get exposed to high G's. Okay, so that's one, for the passenger comfort. For the general appearance, there should be harmony between the slope or the grade and the curve. Okay, so we had to address these criteria as well as the stopping side distance criteria. So these are the design criteria. Okay, so the length of the sag curve for passenger comfort should be greater than or equal this value, and for drainage it should meet this requirement, and for appearance it should be, that's the minimum length. For the headlights stopping side distance, that's the equation that we use. That's a short form. If the stopping side distance was less than L, if the stopping side distance was greater than L, then we substitute in this form. Okay. The last item for designing, or the last criteria for designing vertical curves, which is basically the undercrossing clearance, especially for truck drivers, because they are at seated high relative to the so their line of sight might be obstructed due to the bridge. So we need to make sure that the undercrossing clearance is sufficient for truck drivers to be able to see with the stopping distance available. So the side distance greater than length of vertical curve. Okay, we use this formula. Okay, and H, remember here H is different. H is 2.4 meters, and the obstacle is still the same, didn't change. And this case for a stopping side distance less than L. Is that clear? Okay, so these are basically the quick review for the design criteria for vertical curves. Then we moved on to the pavement design and construction, and we discussed here the function of pavement. And what is pavement? Pavement basically are the layers above natural ground that we add for, so that, to distribute the load on the natural ground. So the definition of pavement in terms of highway design, it means the total thickness of road, including surfacing, base, and some base. Okay. In other words, pavement includes all structural layers of road structures laying on subgrade of the road. So everything above the natural ground,
دكتور
this
سؤال
is
ممكن؟
pavement. Yes.
البيفمنت دكتور اللي هو السب كورس والاشياء هذه او الرصيف؟
لا، البيفمنت اللي هو الطريق. اي شيء فوق الارض الطبيعيه this is considered pavement.
انكلود دكتور الليارات حق الشارع زائد الرصيف.
الرصيف this is a sidewalk, that's another issue. Sidewalks are in urban areas, so sidewalks are sidewalks, but we're talking about pavement, the one that vehicles drive over. This is pavement. Okay, so all the layers above the natural ground, this is pavement. Okay. Okay, what is the functionality of the pavement? The primary functionality for the pavement is to transmit and distribute traffic wheel loads on the to the natural ground. That's basically it. Transmitting, as I mentioned earlier, the wheel, the load of truck wheels are heavy on natural ground. So, that's why we need to have a way to distribute this load over, larger area. It's similar to designing foundations. Okay. And the problem becomes more, vivid in case of runways and aircrafts, because the wheel load of an aircraft is much higher than the wheel load of a truck wheel. Okay. So the design parameter for pavement, we have first the traffic loading. Okay. The subgrade, the nature of the natural soil and its characteristics in terms of bearing capacity and so on. The pavement type and the construction material. So if we are talking about flexible pavement, which is asphalt pavement, that's there is a special design criteria for that. If it's a rigid pavement, like in the case of runways, okay, then it has a different design criteria. Clear? So we start with the traffic load. So the traffic load, this is kind of maybe confusing for some engineers, but for because you can see different trucks, different vehicles, different. Okay, so basically what we do, we take all these trucks, okay, and convert it into equivalent single axle load, number of equivalent single axle load, where the standard single, it's 18,000 pounds or 80 kilonewtons. So some of you might be wondering, okay, how can we do this? It's very simple. Basically, there's an estimate in the DMVs, في إدارات المرور يا شباب. Okay, you can get statistics on the type of trucks that we have licensed. Okay, and these licensed trucks, we assume the worst case condition that it's fully loaded. Okay, and we assume, based on the number of trucks or based on the traffic volume on the road, we have a volume and we have percentage of heavy vehicles or trucks. This percentage basically plays the major role in designing the pavement layers. The passenger cars usually plays a very minor factor in terms of designing pavement layers. The governing factor is trucks are, is a truck load or the truck percentage. Clear? For runways, the situation is different. Runways is not like highways in terms of the design loads. Here we look for the load configurations and the configurations of the wheels. Okay, so basically it's different than pavement. In the highways we look for the equivalent single axle load and this, but for runways the situation is different. Okay, and based on the classification of the runway and the type of aircrafts that it can accept, okay, we make that design. As I mentioned, the wheel configuration plays a major role in the overlap between wheel loads and the subgrade, as you can see in this diagram. Okay, so that was the first part. That was for the axle, the load parameters. Now the second, which is basically the design parameter for subgrade, the natural soil properties. Okay, so basically what we are interested in is the California pairing ratio (CPR) and the resilient modulus (MR). These two are the major inputs in most of the design methods for pavement layers. Okay, what are the criteria that we prefer to have? Basically, this subgrade or the natural soil is the foundation of the road. It's important for structural and pavement life. It should not deflect excessively due to dynamic loading. Okay, it may be infill or embankment. Okay, we might have an infill if there is a cut and fill in the vertical alignment. So what are the pavement types? We have flexible pavement, which is the asphalt pavement. That's what we see every day. And there is the rigid pavement, which is basically a concrete slab, and there might be underneath there may be a layer of sand or gravel or crushed stone. Then that's a natural soil. However, in the asphalt or the flexible pavement, we have multiple layers. So usually we have a base layer, okay, of sand and gravel. Then we have a layer of asphalt, that's a base course. Then we have the surface layer, and there are tacking layers and other layers in between, sealers. So this is more descriptive. As you can see here, these are the layers. That's the natural formation. That's the sub-base. It's common for both. But for the flexible pavement, we have a base course, we have a surface course, and we have surface dressing. This kind of, to make the pavement a little bit smoother. For the rigid pavement, it's just two layers. We have the sub-base and we have the concrete slab. This slab might be plain concrete or reinforced concrete, either way. It depends on the type of loading and the nature of the natural formation or the soil. Okay. For rigid pavement, as we can see, there is a difference because flexible pavement, the load is concentrated right underneath the stress is concentrated underneath the load. But in the rigid pavement, it's distributed all over the slab. It's like, designing a slab carried by the subgrade. In this table, we have a comparison between pavement types and the stress distribution. Okay, and the design for example, flexible pavement, the design principle, it's empirical methods. Okay, but for rigid pavement, it's usual. It's based on elastic theory, like what you do in reinforced concrete design. For the material for flexible pavement, it's granular material. For rigid, it's made of cement, concrete, either plain or reinforced. or even sometimes pre-stressed concrete. For the construction, flexible is constructed of a number of layers. Here it's basically laid slab with steel reinforcement or not. The stress transmits vertical and compressive stress to the lower layers. Here it's the stresses generated are tensile stress because the load, if you apply here, it generates tensile stress here. But for the flexible pavement, if you apply a load here, it gives a stress compressive load this way. Okay. For normal loading, there is an elastic deformation. For rigid pavement, it acts like as a beam or cantilever, as we mentioned here. I'm sorry, for the stresses, transmits vertical stress. Okay, no, we are past with this. Excessive loading. In case of excessive loading, there is local depression. That means there is permanent deformation in the pavement like this. But here, okay, on the surface of the pavement, you will have cracks generated if there is an excessive loading. For temperature, there is no stress generated in flexible pavement. However, for rigid pavement, usually there is thermal stress produced from temperature variations. Okay. The last item, which is opening to traffic. In flexible pavement, we can open it to traffic right after pavement by maybe 24 hours. But in rigid pavement, we might allow sufficient time for the concrete to cure. So usually we leave 14 days for concrete curing. So these are the basic fundamental differences between flexible pavement and rigid pavement in different aspects. Here we have, in this figure, we are showing the elements of rigid pavement. As we can see, it's basically a group of slabs that are separated by joints. We have longitudinal joints, we have transversal joints, we have dowels and tie bars connecting between these different slabs in order to maintain the same behavior and this kind of behavior. Okay, that's another figure. As we can see, the slabs are divided into 10 meters length average, and the width, it's around maybe 5.5 meters for the longitudinal division, as we can see. Okay, now as we mentioned, we have joints in the rigid pavement. So we start with the contraction joints. These contraction joints are made on purpose to weaken areas or weaken points to limit the cracking of the pavement, to these of the concrete to these points. Okay, you have studied concrete, and you know that after we place concrete or pouring the concrete, okay, there is shrinkage that happens. There is a contraction, okay, due to the loss of due to drying, okay, and due to temperature change. So instead of having the surface of the rigid pavement cracked like this, okay, simply what we do, we make these contraction joints. So how we make these contraction joints? Basically, I'm gonna just give you a cross section here. So that's a cross section. Okay, we make a groove here. These grooves will make this section weak. So if there is any cracks, is gonna start here. Okay, so some might say, okay, Dr. Weil, this way this crack will allow, you know, water to go underneath the concrete and disturb the natural soil, and maybe, you know, okay, we say that we seal this groove, okay, with bituminous material to prevent water from leaking underneath, okay, as I mentioned here. Okay, so the purpose of contraction joints prevent the formation of irregular cracks due to restraint, okay, in free contraction of concrete. They are also provided to relieve stresses due to warping to permit the contraction of the slab. Okay. Longitudinal joints. As we mentioned, longitudinal joints, these are lanes are jointed together by joints known as longitudinal joints. Basically, if we have a highway and there is two lanes, usually we make each lane in a different slab. Okay. What's the function of the longitudinal joints? Okay, they are provided normally at 3.5 meters center to center to relieve stresses due to warping, okay, to allow differential shrinkage and swelling, to prevent longitudinal cracking. Okay. Okay, the procedure of construction, initially joints are cut. Again, it's similar to what we have explained earlier, that we have, it's cut, the slab is cut 1/3 slab initial joints to cut to the depth of 1/3 of the slab thickness. Okay, then we fill it with a bituminous material or something. There is the third joint, which is basically the expansion joints. The expansion joint, this is different than these other joints, and usually we stop the concrete by a barrier here. We put a barrier, but before this we put a dowel. Okay, then we, you know, pour our concrete and finish this part. When we remove this barrier and we put here a foam layer or a flexible material. Okay, then we put a jacket or jack here around this dowel bar with a lubricant. Then we start, you know, putting our concrete back here. So what's the purpose of this? Is basically it allows expansion and contraction of concrete without transmitting stresses. So this black thing, this is the rubber most probably. Okay, and the dowel will be something like this. It's fully attached to the concrete here. Okay, and on the other side there's a metal, you know, casing like this, and there's a lubricant here. The purpose of this lubricant is to allow this part to go freely backward and forward, okay, from the dowel, but it's tight enough to transmit shear. So basically this connection allow shear transmission, okay, but axial force, no axial force. Okay, so it's kind of similar to what you had in structural engineering, like this. You know what this? That's a roller. Okay, any questions so far? The last connection, which is basically a construction joint. This joint, you know, typically during construction you cannot, you know, pour concrete all over for the entire projects in one day and continuously. So there is usually a stopping point, and this stopping point we maintain it by having a dowel. Dowels placed should be planned ahead of time, and there are dowels placed, and there is a wooden layer that we put in plate that we put it here to stop the scab. Okay, then in the next day we remove this wood and we continue, and at this joint we open this section and we fill it with sealant. Okay, in this diagram we can see the different dowels and tie bars between longitudinal and in longitudinal joints or construction joints, as we can see in this image. These are real pictures, okay, and you can see that, but this is a reinforced layer or the reinforced rigid pavement. That's again the transversal joints, okay, and you can see the dowels and the rubber here. Any questions so far? Okay, we're going to take a break now and we'll be back in 10 minutes.
Okay.
Last time, okay, before the break we stopped at the rigid pavement construction and we continue from here. Basically, the first step is leveling the subgrade, to match if there is a cut or fill, we do that, and at this stage, okay. Then after the leveling, we go to the subgrade compaction, and that's very important actually if there is a fill, because the subgrade, if we have maybe a 1 meter or 2 meter of fill, this must be done at layers, 25 centimeters each layer. At maximum you can take up to 30 centimeters, but more than that things will get messy, okay, especially if it was a critical major road connecting, that will be carrying a lot of trucks and so on, then we have to be very careful. If the compaction is not correct and it was not tested, that will result basically in permanent deformation in the pavement later on, and you have to readjust for that, which is going to be a very costly job to do. After that, we start placing the sub base, which is crushed stone. The purpose of the sub base, it makes the concrete layer, or the thickness of the concrete layer smaller. We can eliminate this sub base, but at this point, instead of having a 12-inch slab, you can have 18-inch slab, which is not just costly, but it creates problems in terms of curing, shrinkage, construction. It's not highly recommended, okay. So the 12-inch, which is 25 centimeters slab thickness, this is easy to handle, and in terms of shrinkage and thermal stresses, which actually it's a major issue here in Saudi Arabia, okay. So we try to avoid thick slabs here, okay. In order to avoid these thick slabs, we need to have a good sub base underneath the concrete slab. Then again, after having this sub base, it must go into compaction, and this must be compacted, very well compacted, okay, because this is going to be carrying a good portion of the load. And as you can see here, okay, these markers we use it, to lay out the heights of the and the elevations, and so this is gonna be guide for for the compaction process, and to make sure that the vertical profile is constructed correctly. And as you can see, each of these markers are at a station, and usually these marks at maybe 10 meters apart or 5 meters apart. It depends on the level of accuracy that we are looking for. These are the last step, which is basically placing the concrete, and this is concrete paver. Okay, and as you can see, the concrete is poured from here, and this goes to level it and compact it. Okay, there is another technique which similar to the asphalt finishers, which is basically an equipment like this, and from that end the concrete is poured and it goes this way. Okay, and actually it pour the concrete, it place the concrete and compact it, and make a finishing for the surface finishing and all these aspects. Sometimes we need to do a finishing, okay, or touch up on the pavement using this equipment. However, for runways, okay, after finishing and after everything, we use this machine to create grooving the runway surface. And as I mentioned before, the grooving of the runway, the purpose of this grooving is basically to avoid development of hydrofilm, to drain the runway from any rainwater or something like that. That was it for the rigid pavement. Now for the flexible pavement construction. It's quite similar, by the way. Okay, so the same step, subgrade leveling, then compaction of the subgrade, okay, the same procedures. Then laying the subbase, okay, and compacting the subbase. And from here the situation starts to be different from the rigid pavement. First we start with a prime coat. This coat, the purpose of this coat is basically, it's kind of a bituminous material, and it seals the subbase, okay, from rainwater, from water, from moisture, okay, to maintain it, intact. Then after coating the subbase, we start placing the base course, which is basically an asphalt concrete, but it's very granular, and if you drive over it, you will hear loud noise in your from your tires. Okay, so basically the asphalt comes from the batch plant, and they put it here in this hole, and this machine goes forward and place the asphalt and compact it partially. Then there is followed by compactors, as we can see here. These compact the pavement and make sure that it's at the density required. Then after that we go to the surface layer, which is basically the smooth layer of asphalt that we usually drive over, and these the same equipment, but the type of the mix is different, by the way. And as you can see, these are markers to make sure that we are meeting the levels needed for different stations. You will see these at different stations. These are the markers. You can see it here also. I think no, I can't see this, only this one. Then after that we do the marking signs, which is basically finishing. Okay, that's the pavement marking. Then it's open to traffic. Any questions so far? Okay. Key aspects of pavement construction for site engineers. For site engineers, the key aspects are basically these are the important issues for you as a construction engineer to pay attention to. First of all, the geometric layout. The geometric layout is critical for you in terms of the cut and fill. The fill is very critical because it needs compaction. If there is a fill with poor compaction, then the project is a failure. Okay? Then the super elevation, especially for horizontal curves. This is very critical during construction. The subgrade soil. You must be aware and paying attention to the kind of soil during the leveling. If there is any change in the shape of the soil or in the properties of the soil, you have to notify the consultant with what you are seeing on the ground. Okay? The bearing capacity of subgrade soil by having a CBR, California Bearing Ratio, and the subgrade compaction quality control. Again, quality control for compaction. Usually we use sand cone test. There are other technologies that are more reliable than sand cone test because sand cone test it's vulnerable for unfortunately either for human error or for foul play, as I will mention later. So for the cut and fill, as I mentioned, if there is a fill, it must be in layers of 25 centimeters, okay? And usually we try to avoid, large fills, okay? And if it's 1 meter, it's 4 to 3 layers. We do this. And each layer we must have, quality control and samples and stuff. So it's very timely to do fills. However, cuts are relatively, easier, but where you are gonna get dispose of this amount of soil, that's very critical also and very questionable. The optimum section, if you have cut and fill in the same site, this is what we prefer. If we have cut and fill in the same site, that will be optimal condition, so you don't have to worry about disposing this amount of cut. That's another example for cut and fill. And usually if the fill here, we add more fill widening to stabilize the main fill. The subgrade soil, the desired properties in subgrade, stability, that's one of the properties that are desired in soil. Incompressibility, for example, sand is incompressible. However, clay and silt are a little bit compressible. Okay. Permanency of strength. Okay, that's another issue because there are some soil, some types of soil. It's very strong, it's very good, but once it gets some moisture, the whole story becomes different. Okay, like swelling clay and quicksand. Some of these. Different types of soils. Minimum change in volume and stability under adverse conditions of weather and groundwater, as I mentioned before. Good drainage. One of the good soil for good drainage is sand. But if we have, clay, clay is poor in drainage. Okay, ease of compaction. Again, sand, crushed stones, stuff like that, it's easy to compact. But for clay and silt, it's difficult in compaction. Load bearing capacity, it's affected by degree of compaction, moisture content, and soil type. The moisture contents affect subgrade properties like load bearing capacity, shrinkage, and swelling. Okay, shrinkage or swelling. Shrinkage, swelling, and frost heave will tend to deform and crack any pavement type constructing over them. So we try to avoid swelling clay, okay, or any shrinking soil. And the best thing to do, especially for flexible pavement, is the prime coating. We put this prime coating to seal, okay, the structure underneath, underneath the pavement. So if there is water, it will stay away from, if this is our pavement, this is asphalt, and there is a sub base and there is a natural ground, we try to have this sealer here to make sure that no moisture will go through. Okay. Actually, we cannot assure that this is not going to happen, but we try to minimize it. Okay. And if it happens, then we have to act fastly and just repair it. We don't leave it for, a year or so. Otherwise, it starts expanding. Subgrade soil, we have the AASHTO classification, and we have discussed that, and you have studied that before in the soil mechanics course. So that's the AASHTO classification. Okay, and you had an example on that in classifying different soil types. Then we move to compaction, and basically compaction is critical again, and we have different methods for compaction, for testing compaction. There is the core test, okay, there is the sand cone test, which is very common, and there is a nuclear gauge. This is most reliable method. Okay, the sand cone test, it's it's subject to errors. For example, if the person that is taking the sample forgets some soil or some soil added to the sample, all the results will be, bogus. It will not be accurate results. Okay, so we have to be very careful with sand cone testing for the density. For the nuclear gauge, it's more reliable, but it's very expensive actually to have this equipment, and we might need it or use it in critical sites. Okay, there is the plate bearing test, and there is the Bomage EV. That's also dynamic kind of testing for the compaction and the density. Then we discussed here the sand cone method. Okay, and basically it's very simple. We have this plastic jar that contains specific sand that is calibrated, and we know the specific density of that sand, and we have this cone connected to this jar, and it's of a known size. And the test, simply we go and dig into the pavement, into the compacted layer, for almost a hole of 6-inch diameter and with the depth of 6 inch. Then we take the extracted material saved in a container. Okay, يعني يا شباب احنا بنحفر حفرة، تمام، قطرها حوالي 6 انش وعمقها 6 انش، والكومباكتد سويل ده بنجمعه ونحطه في كونتينر، تمام، وبعد كده بناخد المعمل بنوزنه وبنشوف وزنه قد ايه. Then we have this plate, we put it.
دكتور، وزن المحفور اللي القطعه اللي حفرتها انت، هذه اللي حفرتها او شيء ثاني؟
الاختبار ده بيتم ازاي يا شباب؟ اوكي، بنحفر حفرة قطرها حوالي 6 انش، تمام، 6 انش يعني بنتكلم في تقريبا 15 سنتي. تمام. بناخد العينه بنحطها في كيس وبنقفل عليها ونديها رقم اللي هو رقم الموقع اللي احنا اخدناه منه. تمام. بعد كده بنجيب الجار ده، البرطمان ده بيبقى برطمان كبير كده ومليان ساند معاير وفي كون متوصل في اخره. تمام. بنوزنه. so we have W1 وبعدين نقلبه على الحفرة بهذا الشكل. تمام. ونفتح ده المحبس ده فبينزل الساند ويملى الايه الحفرة وبيملى الكون نفسه. بنقفل الجار ده وبنشيله وبنحسب W2 ناخد الوزنة التانية. تمام. طيب الوزنة التانية فيها ايه يا شباب؟ فيها الفرق ما بين الاتنين دول.
الساند اللي نزل.
الساند اللي نزل والساند اللي نزل ملا فين؟ ملا الكون وملا الحفرة. صح؟ يبقى دلتا دبليو هيساوي ايه؟ weight of sand in the cone and hole. صح؟ مظبوط يا شباب؟ طيب
ايوه دكتور مظبوط.
انا الفوليوم تبع الهول عندي والجامة بتاعت الساند عندي. صح؟ يبقى اقدر اقول ايه؟ ركز بقى معايا. الفوليوم سوري الفوليوم تبع الكون معروف. الفوليوم تبع الهول اللي هو ده هنا في اتش هتساوي ايه؟ ايكوال وات؟ هتساوي ايه يا شباب؟ انا لو قسمت الدلتا دبليو على جاما ساند هيديني ايه؟ حجم الساند اللي في الاتنين. صح؟ هطرح منه الفوليوم تبع الكون يبقى انا عندي الفوليوم تبع الهول. واضح؟
واضح يا دكتور.
يعني انا دلوقتي عاوز اشوف الفوليوم اللي يعني دلوقتي الفرق الوزن ده من ده بيديني ايه؟ الساند اللي مالي الكون واللي مالي الهول. صح؟ الفوليوم بتاع الاتنين هيساوي ايه؟ وزن الساند اللي هو الفرق ما بين الوزنين على الدنسيتي بتاعت الساند. صح؟
بالضبط.
بالظبط. بطرح منه الفوليوم تبع الكون بيطلع لي فوليوم تبع الهول. يبقى الجامة بتاعت السامبل هتساوي ايه؟ الوزن اللي احنا طلعناه هنا اللي هو بتاع السامبل الويت تبع السامبل على الفي تبع الهول.
الفوليوم.
بس فيري سيمبل. واضح؟ في هنا اكزامبل.
واضح يا دكتور.
اوكي. وبنشرح فيه الايه بس انا زي ما شرحت لك قبل كده اتس فيري سيمبل يعني. اوكي. في عندنا
دكتور
اكزامبل.
ممكن سؤال دكتور.
اتفضل.
الان الدكتور الان الحفره حفرتها بقطر معين وبعمق معين، ليش احسب الفوليوم مره ثانيه؟ انا عندي القطر وعندي العمق.
اوكي. القطر is not accurate. احنا بنحفر بقطر معين. تمام. عشان يبقى reasonable sample size. يعني ما حدش يجي مثلا يحفر لي حاجه قد كفه الايد ويحسب لي منها يبقى الايرور فيها عالي. فهمت يا سالم؟
بدر يا دكتور بدر. ايوه
بدر.
فهمت يا دكتور.
فهمت يا بدر؟
بس انا قصدي حيكون نسبه تغير جدا بسيط، يعني بين
ازاي؟
الاكتشوال والرقم اللي انا اخذته.
انا هسألك سؤال. لو انت بتحفر في الارض طبيعي كده هتقدر تظبط الحفر بتاعك مظبوط؟ استحالة.
بالملي لا، صعبه.
بالظبط. تمام. هنا لو حصل اختلاف في مثلا 10 سنتيمتر مكعب. اوكي. وارد جدا. انت مش انت ما بتحفرش بسكينه واخد بالك بالظبط وجايب المقاسات بالظبط. فهمتني قصدي ايه؟ استحاله. اتس سويل. تمام. لكن هو الفكره لما بيقول لك احفر around تقريبا 6 انش وعمق تقريبا 6 انش. تمام، عشان السامبل سايز يبقى ايه، حاجه ريلايبل، يعني عندنا جود سامبل. فهمتني الفكره ايه؟ ده الهدف منها كلها. واضح ولا مش واضح؟
تمام دكتور، واضح. نعم واضح.
اوكي. هنا ده W1 وده W2. الفرق ما بينهم كام يا شباب؟ حد يحسب لنا الفرق؟ 6.83 minus 4.26
2.57.
2.57. تمام. طيب الويت اوف ذا سامبل ده W سامبل اهو. الدنسيتي اوف ذا ساند 1.6، يبقى V هول هتساوي ايه؟ الويت ده 2.57 divided by 1.653. اوكي، خلي بالك 1.653 طن بر متر كيوب equal 1.653 كيلو جرام بير لتر. كوريكت؟ مش الطن في 1000 كيلو جرامز والمتر كيوب في 1000 لتر، صح؟ يبقى
صح.
1.653 tons per meter cube equal 1.653 kilogram per liter. So this way we get the volume of the sand, which covers the cone and the hole. طب نشيل منه الفوليوم بتاع الهول 0.667، يبقى ده divided by 1.653 minus 0.6667 يطلع لي 0.888. اليونتس ايه يا شباب؟ لتر. يبقى جاما هتساوي ايه؟ 1.432 divided by 0.888 هتساوي في 1.42 1.599 اللي هو تقريبا 1.6. okay, and here it's kilogram per liter or 1.6 ton per meter cube. واضح؟ simple and easy.
واضح.
اوكي. دايما يا شباب خلوا بالكم من حاجه، ان دايما يكون في عندنا reasonable interpretation for the number. اوكي، يعني هنا السويل طلع لي 1.6 طن بر متر كيوب والساند it was 1.653. So these are reasonable numbers. So we have to look into the values and make sense of it. اوكي، اي سؤال يا شباب؟ Okay, I think that will conclude our lecture for today, and wishing you all the best and see you on Sunday. Okay?
دكتور بالنسبة للتحضير يا دكتور معلش.
Okay, hold a second.